After studying this module, you shall be able to know about the thermodynamic stability of the complex, learn the stepwise formation of complex and stability constant, identify the trends in stepwise formation constants, evaluate the factors affecting the stability of the complexes. Introduction. Stability constant of metal complexes are extremely important. In theoretical chemistry, relationship must often be found between such quantities, and certain properties of the metal ion or ligand stability constants are widely used in analytical chemistry in devising new methods or estimating interfering effects. They must also be considered in such areas as the kinetics of the reaction in solution involving metal complexes, the biological effect of metal ions, etc. Complexation reaction in aqueous solution is substitution reaction, where ligands replace solvent molecules such as water from the coordination sphere of the metal ion. However, the number of water molecules replaced need not be the same as the number of ligands added, because in some cases different coordinated species may have different coordination number around the central metal ion. In this equation, water molecule is present in large axes, so it can be omitted from the formula. In polynuclear complexes, in complexation reaction, those ligands which can act as bridge between the metal ions may form polynuclear complexes. In addition to polynuclear complexes, other species, for example, mixed ligand complexes like hydroxo complexes, protonated complex may also be present. However, we shall discuss at the moment only in the case of polynuclear complexes. Let us get introduction about the stability constant. The equation represents the interaction of complexing agent with the metal ion can be represented as MM plus Na, giving you MMAN. Applying the law of mass action, beta naught Mn is equals to the concentration of the products divided by the concentration of the reactant species raised to the power to their stoichiometric coefficients. The law of mass action is valid only when the activities are used instead of concentration, because the activity of a species is equal to the product of its concentration and its activity coefficient. We have the above relation between the stoichiometric equilibrium constant involving the concentration and the thermodynamic equilibrium constant involving activities, where the curl bracket represents the activities of different species involved and beta naught Mn is thermodynamic overall stability constant. Terms in the square bracket denotes the concentration function as the activities of the species involved in the reaction, and beta Mn is the stoichiometric stability constant. The activity of a particular solute approaches the concentration as the system approaches a certain limiting state chosen arbitrarily. In case of standard activity scale, this limiting state is the pure solvent. Thermodynamically, equally well-defined and useful activity scale can be obtained by choosing a mixed solvent or a solution of a salt as a limiting state. Only stability constant referring to the same activity scale can be directly compared. It is evident that the calculation of thermodynamic equilibrium constant requires either the knowledge of activity coefficient or at least they should be kept constant. For the ions of which do not take part in the formation of complexes, it is possible to create an ionic medium. This is done by adding a large amount of supporting electrolyte, which remains approximately constant even if the concentration of complex forming ions are varied. In such a medium, that is, the medium of constant ionic condition, the activity coefficient might be regarded as constant and stability constant are valid only for the medium used. Now let us have the detailed view of stability constant. Usually, the complexation reactions are studied in solution under specific conditions and the bond energies are calculated, and since the absolute bond energies refer to the gas phase equilibria by M plus A in equilibrium gives MA. MA plus A in equilibrium gives Ma2. However, such studies require the data on hydration energies of the ions, which can be determined reasonably well. Relation between beta and K are beta 1 is equals to K1, beta 2 is equals to K1 into K2 and so on. By successive substitution, you can see we have the equation, the concentration of MAN is equal to K1 into K2 up to Kn into the concentration of M into concentration of A raised to the power of n. Denoting the products of the stepwise products constant by beta, we have beta n is equals to the concentration of MAN divided by the concentration of MAN minus 1 into the concentration of A, where beta n is called the overall stability constant of the nth complex. Log beta n is equals to log K1 plus log K2 plus log K3 up to log Kn, which is equal to the summation of log K1 from 1 to n. The formation of complex MLN is written as MAN minus 1 plus A, giving MAN, with the step stability constant Kn defined as Kn is equals to MAN divided by MAN minus 1 into concentration of A. The overall stability constant beta n for the reaction defined as the concentration of MAN divided by concentration of M into concentration of A raised to the power of m, and is related to Kn as beta n is equals to K1 into K2 up to Kn. The standard free energy delta G naught is given by minus 2.303 RT log beta n, since delta G naught is equals to delta H naught minus T delta S naught. On substituting equations, we get minus 2.303 R log beta n is equals to delta H naught by T minus delta S naught, where delta H naught and delta S naught are the enthalpy and entropy changes during the reaction. For ionic liquids, the value of enthalpy change in aqueous solution is plus minus 20 kilojoules per mole, and for neutral monodentates, the enthalpy change value is 0.20 kilojoule per mole, whereas for the polydentate, this value is up to minus 85 kilojoule per mole. Delta S naught is usually positive due to the reasons: effect of binding ligands to metal ions is more than offset by release of solvent molecules from the coordination sphere of the metal ion, and whole or partial charge neutralization on the metal ion decreases the solvent dipole ion interaction. The entropy changes are minus 10 joules per Kelvin per mole for the neutral molecules to 80 to 260 joules per Kelvin per mole for polydentate ligands, the values increasing with higher charge on the anionic ligand and higher number of donor atoms. Thermodynamic and kinetic stability. Two types of stabilities are recognized for the complexes: thermodynamic and kinetic stability. Thermodynamic stability deals with the bond energy, stability constant and redox potentials. Kinetic stability discusses rates and the mechanism of chemical reaction, formation of intermediate complexes, activation energies for the processes. Stability constant of a complex is the equilibrium constant for the complex ion formation. Stability of a complex refers to the tendency to exist under the equilibrium condition. It is directly related to metal-ligand bond energies. Thermodynamic aspects of complexes. Thermodynamic equilibrium constant, referring to the standard activity scale, can be obtained by studying very dilute solution of the concentration less than 10 to the power of minus 3 molar, in which the activity coefficient have practically the value of unity. We can study those systems where there is a high background of electrolytes, or study the system in presence of electrolyte by maintaining their ionic strength. Very dilute solution where the activity coefficient can be obtained thermodynamically or empirically. Debye-Huckel theory will not affect the whole system. By determining the equilibrium constant at different ion strengths and then extrapolating to infinite dilution. Method 1 is limited to only very stable complexes which are formed even in very dilute solutions. For studying weak or moderately weak complex, high concentration of metal and ligand must be used. The activity coefficient can be calculated by Debye-Huckel formula or other formulae. But if there are number of species present, for example, in stepwise complexation reaction, there is a lot of uncertainty in the value of these coefficients, and the experimental data may fit widely, varying values of stability constant and activity coefficients. When the values of beta naught Mn is obtained by extrapolation of a series of beta Mn values determined at different ionic strengths, the problem arises as to which function of ionic strength should be used in this situation, whether the values of log beta Mn are to be plotted against I raised to the power 1 by 3, I raised to the power 1 by 2, etc. The deviation of the values of beta naught Mn obtained by different extrapolation methods may amount to several 100%. Kinetic aspects of complexes. The ability of a complex to engage itself in reaction involving the replacement of one or more ligands in its coordination sphere by other ligand is called stability of the complex. The complexes that undergo rapid substitution are termed as labile, whereas those with low rates of substitution are called inert. Characteristics of electrolytes. The electrolytes during finding the stability constant must have the following characteristics. The characteristic of electrolytes are: the electrolyte should be highly soluble, the electrolyte constituent should not undergo redox reaction with metal ion, ligand and complex, the cationic part of the electrolyte should not associate with metal ion, ligand and complex. The anionic part of electrolyte should not associate with metal ion, ligand and complex. The presence of electrolyte should not contribute to property which we are measuring. Most modern workers use the constant ionic medium to calculate the value of stoichiometric stability constant. Moreover, for most purposes, it is required to calculate the actual concentration of free metal ion of the complex species present and not their activity, and stoichiometric stability constant are more useful in such cases. But for such problems, especially in investigation of bond formation in complexation reaction without interference of ionic strength, the thermodynamic equilibrium constant are the ones required. Stepwise formation of complex. Complexation reaction in aqueous solution is substitution reaction where ligands replace solvent molecules from the coordination sphere of metal ion. However, the number of water molecules replaced need not be the same as the number of ligands added, because in some cases different coordinated species may have different coordination number around the central metal ion. In this equation, water molecule is present in large axes, so it can be omitted from the formula. In polynuclear complexes, in complexation reaction, those ligands which can act as a bridge between metal ions may form polynuclear complexes. In addition to polynuclear complexes, other species, for example, mixed ligand complexes like hydroxo complexes, protonated complex may also be present. However, we shall discuss at the moment only in the case of polynuclear complexes. Stepwise formation constant. Complex formation in aqueous solution proceeds in steps. Consider the reaction between a metal ion M and ligand A, where K1, K2 are the equation constant for the different steps in complexation reaction and are called stepwise stability constant, and beta 1, beta 2 and beta n are the overall stability constant for the formation of Ma1, Ma2 up to Man species respectively. In a solution containing a metal and a ligand in general, all complex species Ma, M2, Man will be present in addition to some free metal and ligand. In order to find the values of stepwise stability constant, it is convenient to use a number of formation functions which can be obtained from the experimental data, and these formation functions are in turn related by very simple expression to stability constant. The values of stability constant can thus be easily calculated. In measurement of complexation reactions, the total concentration of metal ion and total concentration of ligand are known either from the mixing of stock solution or from analysis of final equation solution. Tm is equals to concentration of M plus concentration of Ma plus concentration of Ma2 up to concentration of Man. Ta is equals to concentration of A plus concentration of Ma plus twice the concentration of Ma2 up to concentration of N into Man. Relation between K1, K2 and Kn and beta n. Consider the expression for beta 3. Beta 3 is equals to Ml3 divided by concentration of M into concentration of L raised to the power of 3. On multiplying both numerator and denominator by concentration of Ml into concentration of Ml2 and then rearranging, we get the equation for beta 3. Beta 3 is also equals to K1 into K2 into K3. Therefore, beta n is equals to K1 into K2 into K3 up to Kn. Log beta n is equals to log K1 plus log K2 plus log K3 up to log Kn. The overall constant beta is equal to the product of the stepwise formation constant K1, K2 up to Kn. Also, the formation of a complex takes place in various stepwise equilibria. The inverse of the formation constant is called the dissociation constant Kd or instability constant of the complex. The dissociation constant gives a measure of the extent to which the equilibrium representing the formation of complex lies to the right. Trends in stepwise formation constant. With a few exceptions, it is commonly observed that the magnitude of stepwise formation constant decreases steadily from K1 to Kn. This trend is illustrated by reactions. You can see from both the cases there is a steady decrease in the value of stepwise formation constant from K1 to Kn, which is due to the increase in the number of ligands in the coordination sphere decreases the number of H2O molecules to be replaced, and thus the probability of replacement of water molecules decreases. Due to the electrostatic factor, due to the steric hindrance increase with increase in the number of ligands, and due to the statistical factors. However, in some cases, it is found that Kn plus 1 is greater than Kn because of unusual structural change and change in electronic structure of the metal ion. Change in electronic configuration causes the change in CFSE, and the complex with more value of CFSE will be more stable, and the equilibrium constant for that complex formation will be high. Consider, for example, the formation of CdBr complex in the aqueous solution. The formation of CdBr complex with bromide exhibit 4-step equilibrium or stepwise formation constants K1, K2, K3 and K4. The order of stepwise formation constant is observed as follows. K1 is greater than K2, which is greater than K3, but K3 is less than K4, which is contrary to K1 greater than K2 greater than K3, which is greater than K4. Aqua complex of most of the M2 plus ions are octahedral, whereas the halo complexes of cadmium 2 plus ion generally tetrahedral. The reaction for the formation of CdBr are as follows. The last step is favored by the release of 3 H2O molecules, and simultaneously there is unusual structural and electronic configuration change, and thus K4 is greater than K3. Further, consider another example of formation of ferrous bipyridyl complex from aqueous solution of ferrous ions. The formation of ferrous bipyridyl complex ion with bipyridyl takes place in 3 steps, and the order of formation of bipyridyl complex are as follows. The two complexes FeH2O4 bipyridyl and FeH2O twice bipyridyl twice are high spin due to presence of weak H2O ligands having T2G4 Eg2 electronic configuration with CFSE of -0.4 delta naught. The complex ferrous bipyridyl thrice formed in last step is low spin due to the presence of only strong bipyridyl ligands. The complex has electronic configuration T2G6 Eg0 with CFSE of -2.4 delta naught. Therefore, there is a change in electronic configuration and increase in CFSE. Hence, K3 is greater than K2. Formation function. Jerome introduces the function n bar called formation function, which gives the average coordination number of ligands bound per metal ion, which is given by total ligand bound to the metal ion divided by total metal, which is equals to Ta minus ligand not bound to metal divided by Tm. Degree of overall complexation phi. Leiden and Frones have made use of another function called degree of overall complexation phi, which is the ratio of total concentration of metal to equation concentration of free metal ion. Phi is equals to degree of overall complexation gives its relation as 1 plus summation of beta n into the concentration of A raised to the power of n. Degree of formation of a particular complex MAC, another formation function employs as alpha C, which is defined as the degree of formation of a particular complex MAC, formation of total metal in the form of complex MAC, where alpha C is equals to the concentration of CH complex divided by Tm. It is clear from the expression that the function n bar phi and alpha C are independent of total concentration of ligand and the metal and depend only on the value of free ligand concentration A for a particular system. Solution which have same value of n bar but different values of total concentration of Tm and Ta are called corresponding solution. These solution must have the same value of free ligand concentration A and the same value of phi and alpha C. Similarly, solution having same value of phi and alpha C must have same value of n bar or other function and free ligand concentration in particular system. Relationship between different functions. As we know that the degree of overall complexation phi is equals to 1 plus summation of beta n into concentration of A raised to the power of n, On differentiating this with respect to A, we get d log phi divided by d log concentration of A is equals to n bar. If we plot log phi versus log A, the slope of the curve gives the value of n bar. To simplify calculation, it is sometimes desirable to complete when n bar is obtained as a function of A. D log phi is equals to n bar d log A. In this case, the above equation is integrated and the integration is performed graphically by putting n bar versus log A and extrapolated the curve between limits A is equals to 0 and various upper values of A, which is equals to AI, and measuring the area under the curve. If C is known, the value of n bar at various values of A can be obtained by the slope of the curve of log alpha C versus log A, but the result obtained may not be of high precision on account of the difficulty of graphic differentiation. Application of stability constant. A knowledge of stability constant of metal complex gives a quantitative measure of different species present in aqueous solution under different condition of pH, presence of other metal ions, ligands, etc. Such an exact knowledge of composition of the solution is essential for a correct interpretation of optically, kinetic and its biological properties. The value of stability constant is used to predict the condition required for complete and maximum formation of given complexes. Reliable information of this type is of great importance in planning, analytical and separation procedure. Stability constant data is therefore used in analytical chemistry, electrochemistry and biological chemistry. Let us summarize. Stability of a complex refers to the tendency to exist under equilibrium condition. Stability constant is used as a measure of thermodynamic stability of a complex. The extent to which a metal cation combines with ligands to form a complex ion is expressed as terms of formation constant. The inverse of the formation constant is called dissociation constant or instability constant of the complex. The dissociation constant gives a measure of the extent to which the equilibrium representing the formation of a complex lies to the right. Complexes possess two types of stability, thermodynamic and kinetic stability. The thermodynamic stability deals with the bond energy stability constant and redox potential. Kinetic stability discusses rates and the mechanism of chemical reaction and formation of intermediate complexes, activation energy, etc. Stability constant is an important tool and is used in analytical chemistry, electrochemistry and biological chemistry.